So today's speaker is Chiyoko Collins, and she received her PhD from University of Colorado in Boulder in 2011. And then she went to UC Berkeley Space Sciences Lab as a postdoc researcher and then a research scientist. When she was in Berkeley, she was working on the ICON MIGHTI Hackmod Extension product and both modeling and satellite data analysis to study atmospheric coupling processes. And she recently joined CU LASP about a month ago. And so she is now here in Boulder, and she will present today on the seasonal variations of small-scale perturbations and atmospheric tides from ICON MIGHTI. Go ahead, Chiyoko.
Thank you, Nick. Today, as Nick said, I'm going to talk about small-scale perturbations and tides from MIGHTI observations. Our ICON team provided a data set, and Scott and Tom and everyone on this list helped me to get these results. Today's outline is I'm going to talk about gravity waves and background of gravity waves, and briefly introduce a MIGHTI data set that I used. And there's a main two results. One is the MIGHTI gravity wave from 90 to 250 kilometers, and MIGHTI tidal seasonal variations, including the level for products that I've been working on, and at the end, the conclusions. So gravity waves have important roles in driving atmospheric circulations, both in the MLT and lower atmosphere, and also in the thermosphere. So this left side showing the circulations by Pram 2002. This S is a synoptic scale wave, P is planetary wave, and G is the gravity wave. So you can see the gravity wave drive the big meridional circulations and also some downward circulations. And also gravity wave have influences in the stratosphere and tropospheric temperature and the wind. And in addition to MLT and below, gravity wave can be important in the thermosphere. This Eat et al. 2009 included the gravity wave parameterization to the thermosphere. And you can see that there is a strong, this is the gravity wave drag. The eastward and westward drag can exist in the thermosphere. So gravity wave can be generated by convections, orography, and front system. And a recent study showing the secondary generation of gravity wave by dissipation of primary waves, and those can be important for the thermospheric gravity waves. So currently, gravity waves has been studied intensively below MLT regions using ground-based observations and satellite observations. Here's the example of Saber gravity waves. Since I'm going to show the MIGHTI satellite data set, I'm here showing the Saber gravity waves. Saber gravity wave can see the horizontal wavelengths longer than 100 kilometers and vertical wavelengths between 4 and 20 kilometers with this analysis method. Left side showing the 4 years climatology of January and July observations, and top panel, the left side showing the gravity wave peak and the polar regions, and the convective region has 4 spots. And then the peak on the polar region flip side due to the changes of wind in the July. But gravity wave, Saber can get the hot peak in these mountains and convective regions. Saber has another advantage showing the different height of the gravity waves. So if you, this is the July different height. Sorry, I don't have the reference, but this is all by the Prus et al. 2009. Left side is July climatology, 30 kilometers and 40, 50, 60, 70. So as gravity wave go up, propagate upward, this convective peak kind of disappears because gravity wave propagation kind of spread out. So as they go up higher altitude, the hot spot kind of disappears. So those, the satellite observation has been providing the global pictures of the gravity waves. So above the MLT region, there are several small scale studies. So one of the example is Goche observations, show the relative density perturbations and also the wind perturbations. And this is the Forbes et al. Showing the small scale relative density perturbations. So their analysis was getting the small scale perturbations along the orbit and the horizontal scale 128 to 640 kilometers. You can see the seasonal variations. Mainly there's a peak, southern hemisphere is larger, but the annual variation peak in June, July dominated both dusk and downside. So the altitude coverage was 230 to 280 kilometers. So there has been some various observations, but we need more observation of small scale perturbations, variations. And now we have a mighty wind and temperature to cover a wide range of altitude, so we can study how the small scale perturbation changes with height. So for this study, we are using icon observations. I think there are lots of talk before me talking about my icons. I'm going to talk about very briefly. So icon is to study forcing from below and forcing from the top. And they have 4 instruments: MIGHTI, FUV, EUV, and IBM. In this talk, I'm only showing the MIGHTI neutral wind and temperature data set for this work. So this is the one of the example of one orbit of MIGHTI winds, and top panel showing the red line wind, and the bottom is green emission results. And left side, this is the zonal wind, and this is meridional wind. And the bottom side is the green line, and again zonal wind and meridional wind. X-axis is the local time, and Y-axis is the altitude. As you can see that some of the nighttime data at some height are missing. They don't have the data. So in this main part of this talk is only focusing on the daytime gravity wave perturbations indicated by this black box, 10 to 17 LT, which is 10 to 16 LT. For the tidal study, I'm going to briefly show at the end what is using this 95 to 110 kilometers, you can get the full-time coverage of the wind. And also, if you go up in the red line wind, you can get some full-time coverage around 250 kilometers. So we are going to show these 2 layers and also the Hackmod results comparing these 2. Before I go in showing the gravity wave results, this is our current validations of the red line wind and green line winds. Left side is FPI and mighty wind at 200 to 300 kilometers at Havana-Champaign, and blue is zonal wind, and red is meridional wind. So they have very good correlations between the ground-based FPI and mighty observations. For the green line wind validations, this is the comparison with the radar in China, line of sight wind, radar, and mighty wind. You can see the very good, reasonable correlations between ground-based and satellite observations. And this is the mighty temperature validations against the radar observations. And solid line is the icon, and dashed line is the lidar. So where they overlap, this is nighttime and daytime, where they overlap, results agree pretty good. So the mighty temperature and winds are validated, and we are going to use that data set for small scale study. Okay, so small scale, this is the data analysis method that I'm going to use. I'm using. Basically, I use the same method they used for the Saber analysis. So first, we are going to, at the fixed local time, large-scale perturbations, wave number 0 to 4, which include the zonal mean and also tides and planetary waves, stationary planetary waves. We fit the large-scale features, and then we remove that, and residual is considered to be a small-scale perturbation, which includes the gravity waves. So left side is the examples at the fixed local time. You can get the longitudinal observations, and the black dot is the mighty observations, and red line is the wave number 0 to 4 fitting. And residual is, and if you, this is the one height at I think 200 and 100 kilometers. If you plot those with the vertically, you can see some wave-like features. Our method only can see the gravity waves or small scale features longer than 500 kilometers. I was told I should call medium scale perturbations, but for now I'm going to call small scale perturbations. And the vertical resolution is about 2.5 kilometers, so we can see gravity wave longer than that wavelength. So this is the day-to-day variation of small-scale perturbations I got from 95 kilometers to 205 kilometers from January to July 2021. So this is a green line wind from 95 to 150, and the red line winds 160 to 250. There is very significant day-to-day variations, but you can see that in the red line wind, you can see the peak in about June, July. I'm sorry, this is the day of the year, and this 360, x-axis is the day of the year, and this 360 before that is 2020, and after that is 2021. You can see the two peaks in the red line, and the green line wind, you can kind of see the 4 peaks. And from this, it is clear that there's a peak around 110 and 120 kilometers, and the gravity wave amplitude decrease above that. And this is the day-to-day variation, so we are trying to combine them to as a monthly mean. And this is the seasonal variations each month. I take average and include the temperature perturbations in the bottom. So like you show that they see that there's a peak in June, July in the red line wind, and there's a semi-annual variations in the green line wind. So there's a changes of seasonal variations between green line wind, 150 kilometers below and above, and temperature perturbations show the semi-annual variations where the semi-annual variation of zonal wind is shown around this higher part. But there's annual variation is dominated between 90 to 95 kilometers for the temperature variations. So the previous plot is averaged over 0 to 40 north, where we can see the icon observations exist. So here we are interested in how the different latitude small scale perturbations, how the latitudinal variation look like for the gravity waves. So the left top is the red line wind at 220 kilometers, and this is the temperature 103 kilometers, and wind at 110 kilometers, and temperature at 94 kilometers. If you look at the 220 kilometers gravity waves, you see the peak in June, July, as you saw, and then some weak semi-annual variation exists. And there is not many significant latitudinal differences in the seasonal variations and amplitude. And green line wind show the semi-annual variations, and the 15 to 30 north gravity wave are largest, but kind of within this 1 sigma variations. And left side is temperature perturbation showing the clear semi-annual variations. And this also does not show clear latitudinal differences. And this bottom side is 94 kilometers. Again, as we showed before, the annual variation dominate at this height. And for this height, the low latitude is the largest for the gravity wave variations. So it is interesting that the gravity wave variation changes annual variation to semi-annual variations for temperature, and then semi-annual variation to annual variations. So we are wondering why that happened. And previous study, this is Plus et al. 2009, showing the 95 and 100 kilometers Saber gravity waves. Dashed line is Saber, 95, and solid is 100 kilometers. Both height showing the semi-annual variations, but our temperature, this black one is 0 to 15, so it's similar latitude. This is 12 to 12 north, and this is climatology. So there's a different seasonal variations. The main difference between these two is the local time coverage. For this plot, I only use daytime, and their results have all the local time. So we include over the local time for temperature gravity wave, and then we begin to see the semi-annual variations throughout the height, and very similar to the Saber observations for this low latitude observations. So it indicating that there are some local time variations. So we plotting here is the gravity wave vary amplitude at 94 kilometers for temperature and wind. Since the 94 kilometers is the lowest zone of wind can go down from MIGHTI, and this is the day of year. So if you look at the temperature, because we are picking this area of the data set, it looks like annual variation is dominated. But if you look at the overview pictures, you see the very clear semi-annual variations. And also, interestingly, there is a gravity wave larger during the daytime, which I did not expect the significant changes of the gravity wave amplitude. So we are looking more into why it happened. But temperature and both green line wind, zonal wind, show the large gravity wave during the daytime. So we are trying to see why we see semi-annual variations and why the annual variation changed to semi-annual variations for the zonal wind. So zonal wind show clear semi-annual variations and somehow changed to annual variations. So left side is the MIGHTI zonal wind, zonal mean, zonal wind at the same locations of the gravity wave observations averaged all together, but from 95 to 300 kilometers. But we are also interested in how the wind look like below. So we took a SD WACAM for 2020 and to see how the gravity wave wind changes below 95 kilometers. To use the SD WACAM, first we try to compare a 95 to 300 kilometers, which is indicated by this red box. From 95 to 150 kilometers, where the green emissions measurement exists. Below 120 kilometers, there's eastward that matches with SD WACAM. And December and January eastward, and May to August westward, they are captured by SD WACAM, this change of the wind directions. For the above 150 kilometers to 300 kilometers, May to August, SD WACAM do a good job comparing, simulating the westward wind, but January, December, wind direction changes. SD WACAM has an eastward, and the MIGHTI wind has the westward. So there are some differences, but if you look at this wind measurement, when the semi-annual variation changes to the annual variations, the wind direction changes from eastward to westward. So it could be affecting gravity wave propagations around this height. So and then the annual annual variation above the red line wind could be due to the wind also showing annual variations. But from here, in the lower atmosphere, we don't really see semi-annual variation that we see, and we see strong annual variations. So we looking more into the source changes. And this left side is the NCAR monthly precipitations. You see the it's a month and the latitude, and this is the peak in May to August as a peak in precipitations, and this is another peak here. So combining both southern hemisphere and northern hemisphere, they have kind of semi-annual variations in the monthly mean precipitations, and that could be causing both the temperature and zonal wind to have semi-annual variations. And another thing we plotting here is the Brand-Weissel frequency, which is n square. If n square Brand-Weissel frequency is calculated mainly by the temperature gradient. So if n square is negative, it's a convective instabilities. So here is the n square, and this is a monthly mean, so it's kind of hard to tell, but the lower the n square is, the higher probability of being convectively convective instabilities. So the peak large gravity wave from May to August could be related to the wave propagation going through this layer compared to the from September through April. So so far we think a combination of all the wind and then source variations generating this gravity wave features, seasonal variations. So these are the small scale wave studies. Before I end, I'm going to show the MIGHTI tides and Hackmod results. So MIGHTI sampling, this is the MIGHTI sampling. MIGHTI measures zonal and meridional wind from 95 to 300 kilometers. And this is the one of the sampling, and at the 30-degree longitude and local time, and see where the satellite goes through for the latitude. So if from -10 to 40 north, you can need 27 days, but depends on where they are. 27 days is not enough to cover from -10 to 40. So this is the study that we did. X-axis, the size of the window to accumulate all the local time. And as you can see that if the latitude is middle from 10 to about 15 or 20, you pretty much cover, you don't need a 45-day window to cover. This is a black line. You need about 27 days should be enough for you to get over the local time and to get the tide. But if you're edge of the icon observational area, you need this red line indicate to cover about 22 hours local time coverage, you need 35 days. But for our analysis, since we have to calculate tides every day and Hackmod every day, to be safe, considering there's a missing data points, we use 45 days window for now to cover the local time. So Hackmod Extension is we use to extend our icon observed tides to the global field from 50 kilometers to 300 kilometers. Icon Hackmod is very, very similar to Overhyde et al. 2011 for CTMT using Saber and Tidy. It's just that we run this for more daily basis. Detailed Hackmod specifications can be found in Forbes et al. 2018. And I did the sensitivity study published in 2020 if you're interested. So for Hackmod, we use data only between 94 and 105 kilometers and latitude range of 10 south to 40 north. Input is both zonal wind and meridional wind and temperature, and we can get UVT and geopotential height for the TIE GCM lower boundary. For my analysis, we have a DW2 to DE3 for diurnal tides, and semi-diurnal tides, we have SW4 to SE3. Hackmod only consider upward propagating tides, include the effect due to absorption of solar radiations in the stratosphere and troposphere rate and heat release. There is no in-situ wave generations are considered above MLT regions. And this Hackmod is used to force the TI GCM, and this Hackmod output is released as a level 4 products. If you're interested, you can download from Icon website. These are the example of Hackmod extension that we have with Icon. So this is D3 climatology at 98 kilometers, 0 to 360 for 2020 D3. Y is the latitude. So Saber use 6-day window, and you can get 50 to 50 degree coverage throughout the year. And this is the MIGHTI 45-day window results from -10 to 40 north. And this bottom side is MIGHTI Hackmod using this icon tides extend to the higher latitude, and you can get this. You can get similar climatology, and the phase between Saber and Icon matches pretty good, and Hackmod general trend matches well with the Saber observations in the higher latitude where Icon doesn't observe. So this is the Icon sampled. We compare with different models, and including the Icon sampled SD Wacom X, which is forced by I think GEOS 5. Left side is the Icon Hackmod, CTMT forced by Saber and Tidy. Right side is the SD Wacom. This is temperature and wind and meridional zonal wind and meridional wind tides. So overall, the Icon Hackmod and CTMT agree well because both are using similar Hackmod. And SD Wacom showed the peak in September, which is comparable between CTMT and Icon Hackmod. The SD Wacom showed a little bit larger tides in the January, and overall larger, but Icon SD Wacom has larger day-to-day variations. So it's a little bit larger, but overall the climatology is similar. And since I showed before, we have a different height of the tides. We can get the green line wind at the 97 below 110, and also red line tides. So top panel showing the 97 kilometers. This is a MIGHTI D3 at 97 kilometers. And this is a 250 kilometers Icon MIGHTI observations. So the gravity D3 amplitude decreased from 97 to 250. And bottom side is the Hackmod. This is 97 kilometers, and this is 250. So Hackmod is, again, we only force the Hackmod between 95 to 105 kilometers. So we expect this 97 to be similar to the observations, but high altitude, Hackmod does a good job simulating the MIGHTI observations at 250 kilometers. So some components agree well with the Hackmod. Some components is having some difficult time matching with the 250 kilometers MIGHTI observations. So using those different height of the Icon tides, we can do different studies. So left side is so we are showing its diurnal tides, D2, D3, D0, DW2 for 4 different, these results are all at 250 kilometers. Top panel is the MIGHTI tidal variations at this height. And second panel is the Hackmod results at 250 kilometers. And bottom one is TIGCM forced by a Hackmod at the 97 kilometers. And results are at 250. For D3 and DE2, there is no obvious in situ source for these variations. The Hackmod can simulate, reproduce at 250 kilometers tidal variations well, like peak here, and amplitude are very comparable between the Hackmod and the MIGHTI. The TIGCM D2 and D3, the timing is correct, but they tend to overestimate the tides at 250 kilometers. And for the D0 and DW2, the Hackmod does not show any propagations from lower atmosphere. And D0 and DW2 can be generated in situ by nonlinear interaction between the planetary wave and the migrating tides. So those things cannot be included in Hackmod. But TIGCM can include those. So we plot here the TIGCM to 50 kilometers. The D0 may be simulating here okay with the TIGCM, but DW2 is still having not agree well at 250 kilometers. But this TIGCM results are new, and I haven't applied the Icon sampling latitude location. So that's my next step to compare how the Icon sample TIGCM compare with tides. So conclusions, small scale perturbations are extracted from MIGHTI wind and temperature from 90 to 50 kilometers. And semi-annual variation was dominated below 150 kilometers, and large annual variation observed above 160 kilometers. And there's strong local time variations in the gravity wave exist in the lower thermosphere, and those variations are most likely related to both the source and changes in propagations. And MIGHTI ties for D3 and components agree well with Saber and somewhat agree well with the SD-WACAM-X. And if you're interested in getting icon data, including the level 4 Hackmod product, you can go this website. New version 2 Hackmod will be released soon. So if you have any questions, you can ask me. And that's my talk.
Okay, thank you, Chiyoko. Does anyone have any question?
Hi, Joko. I have a question.
Okay.
And I saw your the wind you're showing. I think that's maybe the zonal mean wind, or it shows the almost always westward. Yeah, this one. So
Yes.
is this average? Let me see. So is the average over 0 to 40° north?
Yes.
And
Yes. And
okay.
then during daytime. Yeah, I
Oh,
should.
during
Yeah.
daytime. I see.
Yeah.
Okay, so so that's and the same way of sampling for the Wacom-X
No,
results.
no. Sampling is I just take average over SD-WACAM. So I didn't do the icon sampling. So that could be the one reason it's different.
Oh, so this the Wacom result is all longitude and all local times, not just daytime.
No, SD-WACAM is daytime, but I didn't do the icon sampling.
Oh, I see. Okay.
Yeah.
All right. Okay, thanks.
So Dan Marsh asked a question in the chat. I'll read to you. He was wondering if ICON and Saber data could be combined to estimate the tidal amplitude.
Yes, that's what we are trying. Next step, since we are a little bit having problem with semi-diurnal tides, migrating tides, because they have the peak in the southern hemisphere. We are thinking about combining Saber and MIGHTI to get the better results for the southern hemisphere. Yes.
So in that case, just follow up myself. You would fit them both to the Huff mode. Is that the idea?
That's what we are trying to do next step.
And Anne Smith has a question. Go ahead, Anne.
Hi, Chihoko. This is very
Hi.
interesting. I was wondering for the semi-annual oscillation, did you look in the latitude to see if it's mostly in the tropics, like the semi-annual oscillation lower down, or does it extend into higher latitude?
So this is the different latitude. Different color represent different latitude. For the zonal wind, we see most of the all the latitude showing somewhat similar semi-annual variations, and also this temperature showing all the latitude showing similar semi-annual variations.
Okay, thank you.
Choco, I have another question. So the for the HME, does it use information, for each altitude?
Mhm.
Does it use only the measurement for that altitude to get the tidal the half mode, or it kind of uses all altitude, try to consider all the information and get a of the vertical information
We
as well as the horizontal?
we do yeah, between 95 to 101. We fit the yeah, those together to get the better fit.
So it's a global fit, not just one for individual altitude.
Individual yes, yes.
Okay. Yeah, because I was looking at the last few slides you presented. It seems
Okay.
sometimes they have very different amplitude. Maybe later with the TI. Yeah, this one, for example, the let me think. So D2 and D3,
Okay,
they are not.
they are not
Yeah,
because
go ahead.
because Hackmod we only fit the 90 to 105 kilometers, and above that is not fitting. So
Oh, so above that, what then? What does the half mode do? I mean, the HME does for the higher altitude. Where does it get emission?
we have the Hackmod functions from I think GSWM. So basically theoretical fitting above where we don't have the data set.
Okay.
Yeah, so yeah, that's why we have no institute generation. So we only fit the lower part and we let them go. So, and we are also thinking about fitting the 250 kilometers as well to get the better fit, but we haven't done the fitting the height yet.
Oh, I see. Yeah, I don't know how does it know. For example, the HME for D0 and DW2, it obviously show a very strong decay with altitude.
Right.
Where MIGHTI, seems it's still growing. So how does it know that it would decay? Does it have any information on the molecular diffusion or molecular damping? Is it how it knows or how it deduce the vertical damping?
I think those are included in the model that when they generated the half mode function, but they do not have an institute source.
Okay. I see. So basically, it has a kind of a boundary condition at 90 to 100, and then just using some empirical relation higher above.
Yeah, there's a Hackmod function. If you, I can show you. Yeah, there's a altitude variation. So if you fit the lower part, you just decided how they decay based on the, yeah.
Okay, thanks.
Hi, Chihoko. So you showed that both the wind and the temperature, their seasonal variation change with altitude, and then you also showed that the seasonal variation change with the local time. So in one of the slides where you show the wind and the temperature seasonal variation at different latitude and different altitude, is that one you including all the local time, or just do they have the same local time? Not this one, not this one.
This one?
Yeah, this one. Yeah, are they using the same local?
Yeah, it's only daytime data set, 10 to 16 local time.
Okay, so but this different altitude, different latitude, and the wind and the temperature, they are all using the same local time and including
yes.
all the daytime local time.
Yeah, the local time is same in this part. Yes.
Okay, so would this, if you have data available at more local time, would this change this seasonal variation from annual to semi-annual? For example, for the wind, the red line.
So So we have a data for the wind here. If I look at this, if you include all of it, it's still semi-annual variations for the zonal wind.
For the zonal wind at
Yeah.
like 200, above 200, right?
Here?
Yeah, the red ones at high altitude, the red line image. Yeah, zonal wind.
They still show the annual variations, but this data sometimes is really bad, so we don't have much coverage. But even I include all of it, the annual variation is stronger in the high altitude.
Okay, but does it have also have semi-annual component in it?
They do have semi-annual they do have semi-annual components.
So if you're including more local time, that increase the semi-annual component amplitude?
I haven't looked carefully yet, but like if you see here, you see some semi-annual components. It's just annual variation is dominated.
Okay.
Yeah, I should check. Yeah.
Okay, thanks.
You did show some comparison with Saber, showing the semi-annual variation. With the other observation in thermosphere gravity wave, do they also show the stronger annual variation?
For this one, this Jeff's paper, it depends on the latitude, but this side, this is they see strong annual variations, and this part showing strong annual variations. Here, I think depends on latitude. You see peak here, you see peak here. So some annual variation, for example, here you see the strong in the low latitude. They have the annual variations.
Yeah, and also, you have one slide that shows that from the source of the gravity wave in the troposphere in July, it is more in the northern hemisphere and in the convection zone in the equatorial region, and in July, it's the southern hemisphere and the equatorial region, the convergence and the convection zone. But then when you goes to high altitude,
the Saber, yeah.
Yeah, then when you go to higher altitude, then it's kind of that latitudinal variation kind of smeared out.
Right.
Yeah. Okay. Yeah. So I'm wondering, just is this so basically that from the source it would have more latitudinal difference in the seasonal variation, but at higher altitude, that latitudinal variation of the seasonal variation will be less at higher altitude, seems.
Right, that's what we are seeing.
Okay. But is there a northern and a southern hemispheric asymmetry? The January and the July difference?
We don't have the southern hemispheric data, so cannot really say. But they do. This Goche data set shows some hemispheric differences.
Okay, the northern hemisphere has more gravity wave activity, or southern hemisphere?
Southern hemisphere. This shows southern hemisphere.
Okay. Okay, thanks.
All right, are there any other questions? If not, then thank you again, Chiyoko.
Thank you very much.